Today's lesson is about verifying trig identities. First of all, let's go over some basic trig identities. We have reciprocal identities. We have ratio identities and also Pythagorean trig identities. For Pythagorean trig identities, the most useful is this is the one. But normally we use this twisted form from sin square x plus cosine square x equals 1. We got sin square x equals 1 minus cosine square x. We can factor this. We got 1 minus cosine x times 1 plus cosine x. For cosine square x equals 1 minus sin square x, we can factor into 1 minus sin x times 1 plus sin x. When we do the backwards from 1 minus cosine x times 1 plus cosine x back to this sin square x, or when we have this backwards, go to sin square x. This is a conjugate multiply. Now let's look at some example. First of all, always start with more complicated side and rewrite everything in terms of sin and cosine x. That's the tip 1 for verify trig identities. More complicated side, definitely when you have fraction, that's more complicated side. Therefore, for this verifying trig identities, I will get started from left hand side equals. Change everything into sin and cosine. So cosine x, this is cosine alpha, 1 minus tangent alpha, I turn it into sin alpha over cosine alpha, plus sin alpha over 1 minus cosine alpha over sin alpha. So remember, for tangent alpha equals sin alpha over cosine alpha, and for cotangent alpha equals cosine alpha over sin alpha. Then we need to working on denominator first. Because you have to have a clear division line, you can use the rule for complex fraction. Therefore, top still cosine alpha. And denominator, I put over 1. Then the operation of a fraction, denominator multiply, cross multiply. You will get the cosine alpha minus sin alpha. Then I plus sin alpha. This part I still do denominator multiply, then cross multiply. So I got the sin alpha. Then I do cross multiply, I got the sin alpha minus cosine alpha. This time we have clear division line. I can jump the denominator. Therefore, I got cosine alpha times cosine alpha, that's cosine square alpha. Denominator will be cosine alpha minus sin alpha. Then plus sin square alpha over sine alpha minus cosine alpha. This is an operation of a fraction. We try to make the same denominator. What's the relationship between these two? We know that it's opposite. For a minus b and b minus a, that's opposite. Therefore, I will do negative sign to the top and bottom so that I can change the denominator into cosine alpha minus sine alpha. Therefore, I got the cosine alpha minus sine alpha. Look at the top. I got the cosine square alpha minus sine square alpha. For this part, that's those factoring a squared minus b squared. I can write down a plus b times a minus b. Therefore, I got cosine alpha plus sine alpha times cosine alpha minus sine alpha over cosine alpha minus sine alpha. This time you can reduce and I got cosine alpha plus sine alpha. That's the right side of this trig identity. So I write down equals right hand side. That's all. End of this proof. Now let's look at the type 2. You always remember, start with the more complex side. Involving a fraction means complex side normally. Then rewrite everything in terms of a sine and a cosine. Then if you have a fraction operation, work on that. After you get the clear division line, you can do the operation of a complex fraction. So for this problem, still I need to get started from left-hand side equals. Check over here, we know that sine square theta plus cosine square theta, that's equal to 1. That's Pythagorean trig identities. Therefore, I got 1 plus cotangent square theta equals cosine square theta over sine square theta. For denominator, we have 1 plus tangent square theta equals sine square theta over cosine square theta. So we're working on the fraction on the top and on the denominator. We put over 1. Then we do cross multiply. Denominator multiply, then cross multiply. We got the sine square theta. Cross multiply, we got sine square theta plus cosine square theta. Then look at the denominator. Still, I got the cosine square theta. Cross multiply, that's cosine square theta plus sine square theta. We know this part equals 1. This one equal to 1. Therefore, we got 1 over sine square theta. Denominator is 1 over cosine square theta. Then we do operation of complex fraction. Your denominator drop down. You will get cosine square theta over sine square theta. That's equals cotangent square theta. That's the right hand side. Therefore, we finish this proof. When you verify trig identities, conjugate multiply, very, very useful. In what situation we need that? Only this situation, when you have 1 plus or minus cosine x or 1 plus or minus sine x as the denominator. That's working on 1 over 1 minus cosine x. We know a plus b, the conjugate will be a minus b. So we got a squared minus b squared. Therefore, you will get the 1 minus cosine x times its conjugate is 1 plus cosine x. So we got a squared minus b squared, that's 1 minus cosine square x. Top, that's 1 plus cosine x. 1 minus cosine square x, that's sine square x. Top will be 1 plus cosine x. We call this process is a conjugate multiply. Let's do one more. For 1 plus sine x, conjugate will be 1 minus sine x. So we got the 1 minus sine square x. Top is 1 minus sine x. Therefore, we got the cosine square x. Top will be 1 minus sine x. Let's find the pattern. If you have 1 minus cosine x, which means your sine square x will be the denominator. Top will be conjugated to this one. That's how you get the 1 plus cosine x. If you have 1 plus sine x, that means you need to change into cosine square x, and top will be the conjugate for that. This is the trig conjugate multiply. Try to remember the pattern. When you have 1 minus cosine x or 1 plus cosine x, you are expected to get sine square x as a denominator. When you have 1 minus sine x or 1 plus sine x, then you are supposed to get sine square x as a denominator. Top part will be conjugated to this. See, for this one is conjugated to 1 plus cosine x. These two are conjugate to each other. So when you verify trig identities, whenever you say 1 plus sine theta, means you have to do this conjugate multiply. That's the first priority. Ignore other stuff, working on this. So we get started from left-hand side, equals. Change everything into sine and cosine. It's already sine cosine for first part. Then I'm working on 1 plus sine theta do the conjugate multiply. So I do 1 minus sine theta. 1 minus sine theta. Remember in your mind, when you do the conjugate multiply, you are supposed to get the cosine squared theta. So I keep bring this down because we cannot do anything about that. Then plus. For these two, we got the 1 minus the sine squared theta. Therefore, I just write down here is cosine squared theta. Look at the top, I got the cosine theta times 1 minus sine theta. So reduce, here's 1. This is a cosine theta. Let me bring this down again. Then I have denominator is cosine theta, top is 1 minus sine theta. Since we have the same denominator, I can put this together. 1 plus sine theta plus 1 minus sine theta. Positive sine theta and a negative sine theta cancel out. We got 2 over cosine theta. That is 2 secant theta equals right hand side. So we finish proving. So we have used other strategies when we verify trig identities. First of all, we remember that a plus b squared, square of addition and subtraction, that is a squared plus 2ab plus b squared. So we get start from the left hand side. I have 4 sine squared theta plus these two multiply times 2, that is 12 sine theta cosine theta. Then plus 9 cosine squared theta. Then we're working on this. We got 9 sine squared theta minus 12, 2ab, 12 sine theta cosine theta. Then plus 4 cosine squared theta. Because negative 2 cosine theta squared is 4 cosine squared theta. This one combined like term is gone. So we combine like term, we got these two like term and then these two like term. We got 13 sine squared theta plus 13 cosine squared theta. That will be 13 because sine squared theta plus cosine squared theta, that's equals 1. That's equals to right hand side.